Welcome back. Now that we know a little bit about inclined planes and we know a little bit about friction, we can combine them and figure out what happens to an object when it's on an inclined plane that actually has friction. So let's I guess just do the problem. So this is a 10 kilogram block and it's on an inclined plane with a 30-degree angle. And let's say the coefficient of friction between the block and the plane, I guess this could be a hill or something. Let's say the coefficient of friction right here is 0.5, which actually is a lot of friction. That's the coefficient of friction, 0.5. So let's figure out what happens. So what forces are acting on this, or what's, I guess, pulling on this object, and that's the force of gravity, which we figured out when we did the inclined plane. And I'll draw that vector. It's going straight down. Force of gravity, straight down. And so to figure out this problem, we just have to figure out, well, two things. We have to figure out what is the component of the gravitational force that is parallel to the surface, and then what is the component of the gravitational force that is normal, or not normal, that is perpendicular to the surface. And of course, the normal force would be going in equal but opposite direction, and that's the force that keeps the object from falling into the hill. So let's just work it out. Well, what's the force of gravity, first of all? If we assume acceleration of gravity is roughly 10 meters per second squared, then the force of gravity is 100 newtons, right? 100 newtons, that's what gravity's pulling down. The normal, not the normal, I should stop using, the force perpendicular to the ground, or the component of gravity that's perpendicular to the ground, that's kind of pushing into the ground. I'll do that in green. That force, which would be equal to the normal force, this force right here, what is this going to be equal to? This force is pointing straight into the ground, and of course it's going to be the same as the normal force, which is, I'll do a little dotted line. This is the normal force, and the normal force is just the equal and opposite force to this one. This is what gravity's doing. This is what the hill's doing to keep gravity from pulling the block into the hill. Well, we figured out when we, in the inclined plane, or the introduction to the, what did I call it, the mass on the inclined plane video, that this angle is the same as this angle. This is 30 degrees. Watch that video if you don't believe me. You can think of it conceptually. On an exam, if you forget that this angle is equal to, think about what happens as this plane gets steeper or less steep. The difference between this perpendicular force to the surface and the gravitational force. And you'd realize that this angle and that angle is intuitively the same as well. And if you want to do the proof, remember this is a right angle. This is 90 minus this angle, so this angle has to be this angle. Anyway, I'm probably confusing you. Getting back to the problem. If this is 100 newtons, and this is a 30-degree angle, what is this side? Well, actually, let me draw out the force that's going parallel to the surface as well, so that you realize that this is a right triangle. So that's the force parallel. So going back to it, what's this green force? This force of gravity that's perpendicular. Well, we have the angle, we have the hypotenuse, and we want to figure out the adjacent side, right? So SOHCAHTOA. SOHCAHTOA. Doesn't hurt to write that at the top of your paper to remember. So we're dealing with hypotenuse, the angle, and the adjacent side. So cosine. Cosine is adjacent over hypotenuse. So the cosine of 30 degrees is equal to the adjacent side. So that's what we're solving for. Let's just call that, well, it's going to be the same magnitude as the normal force, so let's call that the normal force. So let's say that's the same thing as this thing. I just need a label, so I'll call it, this is really the normal force, but we're just trying to figure out the magnitude, because that's what matters. The direction is kind of irrelevant. Well, it's not irrelevant, you should think about it, but I don't want to get mad emails from your physics teachers teaching you incorrect things. Well, it's equal to this, the magnitude of this force over the hypotenuse, which is the force of gravity, 100 newtons. So it's 100 newtons, 100 cosine of 30 degrees, which equals the normal force. And the cosine of 30 degrees is square root of 3 over 2. So 100 times the square root of 3 over 2. This is square root of 3 over 2. That's 100 divided by 2. That's 50 square roots of 3. 50 square roots of 3 equals normal force. So the magnitude of this vector is 50 square roots of 3, and the magnitude of this vector is 50 square roots of 3. Good enough. And what's this side going to be? This vector that's going parallel to the direction. It's equal in magnitude to this vector, right? I could have drawn it up here too. This vector. and I just shifted it down here. And you could tell that if this is perpendicular to the surface and this is perpendicular to this vector, then this vector must be parallel to the surface. So what is this? So this is the opposite side, and we have the hypotenuse, so we'll use sine. So sine of 30 degrees is equal to, we'll call this the force, the parallel force, is equal to the parallel force over the hypotenuse, which is 100 newtons. So the parallel force, just multiplying both sides by 100, is equal to 100 sine of 30. Sine of 30 is 1/2. 1/2 times 100. So the parallel force is 50 newtons. And that's what we figured out in the previous problem as well, that the force going in this direction is 50 newtons. And last time we said, oh, well, there's no friction, so we're pulling with 50 newtons is 10 kilograms. So it's accelerating at 5 meters per second in this direction. But this time, there's a slight a hurdle. We actually have friction. And from the friction module, we learned that, one, friction is always going to be acting against the direction that the object is moving. And two, that it's proportional to the normal force, or this force right here, or proportional to the component of gravity that's perpendicular to the surface. And what is that? It's 50 square roots of 3 newtons. So the force of friction, which is always going to be opposite, like f of sub f, is always opposite to the direction that the object is moving, is going to be equal to, force of friction is always equal to the coefficient of friction times the normal force. The normal force is, of course, magnitude-wise the same as the component of gravity. I know I keep repeating it. The component of gravity perpendicular to the surface. So what is that? We know the coefficient of friction is 0.5. And we know that this magnitude and this magnitude, which are the same, is 50 square roots of 3 times 50 square roots of 3 newtons. So 0.5 times 50 square roots of 3. So the force of friction is 25 square root of 3 newtons. So this is 25 square roots of 3 newtons. So the component of gravity that's going parallel to the surface is going in this direction at 50 newtons, and friction is essentially negating a bit of it in the opposite direction, still parallel, but in the opposite direction, going up the surface at 25 square roots of 3 newtons. So what is the net force on the vector, on the object? Well, the net force, let's call this the force subnet. The force subnet is going to be equal to the force of gravity parallel to the plane, which we figured out as 50 newtons. Right, this one, minus the force of friction, minus 25 square roots of 3 newtons. And then if we wanted to figure out, well, let me figure out what that is. So, let's see, 3, take the square root, times 25 equals, let me make that into a negative number, and then plus 50 equals. So roughly 6.7 newtons. So this is equal to 6.7 newtons. So the net force, so friction is negating a lot of the force of gravity parallel to the surface. So the net force is only 6.7 newtons this way. So how fast is the object going to accelerate? Well, 6.7 divided by the mass, right? F equals ma. So 6.7 is equal to 10 times the acceleration. Divide both sides by 10. So 0.67 is equal to the acceleration. That's 0.67 meters per second squared. Actually, well, I don't have space for the units. So that's fascinating. 2 videos ago, when we did the same problem without friction, the object was accelerating at 5 meters per second squared, which is quite fast. That's pretty good acceleration. But when you introduce friction here, all of a sudden, and this was actually a pretty high coefficient of friction, that friction really slowed down the object. And so the object is barely accelerating at 0.67 meters. That's actually still not bad acceleration, but it's accelerating at 0.67 meters per second squared, much slower than it was doing in the absence of friction. And so we could even figure out, what does the coefficient of friction have to be for this object not to move at all, right? And you've seen that. I mean, you've stood on a hill and your shoes didn't slide down the hill, and that's because the coefficient of friction was larger than the force of gravity parallel to the surface, and that's why you didn't slide down the hill on your shoes. Anyway, that's enough for this video, and I'll see you in the next one. See you soon.